All right, let's go ahead and start. Uh, there are some people who are online gonna join from online via Zoom. Yep. I'm teaching software engineering and artificial intelligence. Yeah. I think you took both of them. Artificial intelligence this time and software engineering probably in the last semester. You did? You did take software engineering? Okay. All right. Okay, so let me show you guys the outline of what we're going to cover this week. Machine learning. I think some of you may have already taken machine learning course. This is not very detailed technical explanation of what machine learning is and what are different machine learning techniques. Just, a brief kind of overview of machine learning along with a little bit of an explanation and a code example, program example of uh, a few of the simple scenarios that might be helpful from this course's perspective. So we're going to go over machine learning because machine learning is actually part of or a subset of artificial intelligence. So we will have to cover that. So we'll spend 1 week on machine learning. We're going to talk about basically just like introduce what machine learning is, why machine learning is very important, why we have to cover that. A few of the famous machine learning algorithms, we will just go over those. No technical explanation. Well, not that no technical explanation, but a little bit of understanding of what machine learning algorithms are. And then we'll talk about the classification and regulation algorithms. What is the difference between those, and what are different types of machine learning algorithms that we're going to cover? And I think just because last week I didn't have a chance to provide a demonstration of Bayesian network, if we have time today, we're going to go over Bayesian network a little bit again, how the network is constructed, how you can get the conditional probability distributions, and how you can answer several queries, several questions using your Bayesian network structure. So today we're going to talk more about the theory behind machine learning. And on Wednesday, we're going to go over a couple of examples where we're going to have data in hand and we will write a couple of algorithms or 3 different machine learning algorithms to solve a problem using the data that we have. Okay, Ronald, you had a question. No, machine learning is not different from AI, but AI is a broader, bigger branch of computer science. Okay, and then within AI, machine learning is a part, is a subset of AI. Okay, I have a slide that will explain where does machine learning fit in within the context of AI, artificial intelligence. Okay, so we're going to talk about machine learning, unsupervised learning, deep learning, reinforcement learning. These are all parts of AI. They are the subset of AI, but they use different techniques. The idea behind all of these is to basically design machines, computer programs, agents that mimic the human behavior without giving any explicit instructions, so that the machines can perform tasks on their own by learning from either data or by interacting with the environment to mimic human behavior, and then without giving explicit instructions. Yeah, you can call them autonomous, yes. So before I answer your question in more detail, let's go over basically the agenda for this course and see what we have done so far. I would say that this is week 12, right? The semester has gone just like that. We didn't even realize. We spent a lot of time on search problems, planning, and then we spent about a couple of weeks on markup decision processes, reinforcement learning. There was about, I think, 6 or 7 weeks that we spent on that. A lot of time, almost half of the entire semester that we spent on the first part, the search problems. It's because search also covers a very broad range of AI applications that we have talked about. Well, the first week went over just going through like introduction of AI, when did it start, where it started from and where it is. No, these are just mentioned applications. Yes, that probabilistic reasoning can be used in areas like this. It actually has been used in areas like this. So if you remember when we started Bayesian networks back, I think in week 8, probably, we said that Bayesian networks, it's based on probabilistic reasoning, based on probabilistic graphical models that follow basically certain axioms or theorems of probability. And there is a Bayes theorem that plays a very, very important role in answering several real-world queries. And probabilistic reasoning can be used in several different applications. And we just talked about some of those. Very briefly discussed. Didn't go over detailed examples of probably any of those, but we have talked about, we have covered, and then we covered basically the canonical example, the alarm network that we talked about quite a bit, right? Using Bayesian networks. Alarm network. Yeah. All right. So we spent about 11 weeks in the part 1 and 2, which is actually what is more relevant to the AI applications. And now we're going to talk about the subset of AI. Okay, the subset of AI, which is machine learning. Then we're going to talk about deep learning and computer vision. And towards the end, we're going to discuss how machine learning or deep learning or these AI can be used in natural language processing. Each of them, these 3 weeks has either homework. No, actually, machine learning doesn't have a homework. It has kind of not a homework, but the classwork that I'm going to do in front of you. So I will program a few examples. I'll write some code, design some machine learning models to show you how machine learning works. And then we will inherit several different things of machine learning. And then we will design basically a deep learning program agent that will solve a specific problem. And then we will also design a computer vision application in the class. And then you will be given an assignment to basically take some of that code and then extend it and solve another problem. Okay. And then finally, you will talk about natural language processing also with a homework. So quite a bit that we have already done. I can already see that we have kind of slowed down a little bit, which is good in the course. Some of these assignments, I promise you, they are the best chance for all of you to, if you are falling behind in the first 3 homework activities, these are the best chance for you to just boost up your grade because they are going to be the easiest. Okay, I wouldn't ask you to just simply copy and paste the code that I will write for all of you, but actually use your own reasoning and use your own logic to solve the problem in a better way. Okay, because if you want to be a data scientist, a software engineer, a machine learning engineer, there are several different names in the industry that are now called for jobs like this. Computer vision engineer. Mostly what you will be doing is what we're going to cover today. Mostly these are the practices that machine learning engineers and people in this field, in this area, do on their daily basis. So this is going to be very important. We have talked about, we have looked at this slide in the first lecture, very first lecture, week 1, lecture 1. We said that AI basically is a bigger branch of computer science. And then within AI, there are several subsets, and we actually looked at the AI from a human's perspective, which is why I put an emoji, smiling emoji there. Like thinking from a human's perspective. If you guys remember the 4 parts, when we said that when we defined the AI, and then we said that the goal, for us to make these AI agents is for them to basically think like humans, act like humans, think rationally, and act rationally. If you guys remember the 4 items that we said that, we design agents to follow these 4 traits in order for the agents or the programs or the software to mimic human behavior without being given explicit instructions. Okay, so our goal is basically to make the software or AI agents to think like humans, act like humans, think rationally and act rationally. Think rationally and act rationally comes from the perspective of maximizing the expected utility, okay? Quite a bit of that we have covered in reinforcement learning part, right? So, and then think like human and act like human comes from the perspective from actually neuroscience. It's the field of neuroscience which has been studied for decades and decades. And inheriting the ideas from neuroscience, we actually design machines that are capable of thinking like humans, okay, or acting like humans. Ronald.
So just based on interpretation. They call it's not based on something that's superficial about how humans think, but rather like the actual mechanics of how our brains.
Yeah. So artificial neural networks inherit the properties of an actual human brain, even though we don't fully understand the structure of a human brain. Whatever we have observed so far, okay, in the field of neuroscience, we try to mimic that. And the artificial neural networks that we are going to cover, not today, but next week, yes, when we talk about deep learning, we will see quite a lot of the ideas. We will actually go over the structure of a human brain, what neurons are, how they're connected with each other, how they fire up, how as humans we respond to different events. Okay, so we said that basically, like from this slide, we said if so humans have different several different properties, like through speech, right? Through like speaking some sort of language, we communicate with each other. Okay, that's the area of speech recognition, by the way. Speech recognition, okay? Or natural language processing. So, and using some sort of properties or inherited features, we can read, we can write, et cetera, et cetera. That's the area of natural language processing, right? So this basically comes from statistical learning perspective because it requires a lot of data. So whenever we talk about statistical learning or machine learning, it actually is based on data, or we call it data-driven techniques, okay? Because we require quite a lot of data to provide to the machine to learn patterns, and then to be able to perform, either recognize some words said in a speech, or identify words that are written in a speech in a specific language. Ronald.
Actually, or just operator has to check.
So usually there is a term called in machine learning that your model is only as good as your data that you have in hand. So the better data that you have, the better your model performance will be. So there's quite a bit of effort that is actually spent before designing any model, machine learning model, to perform data cleaning, data pre-processing, so that the machines understand it better, or there is no mistake, there are no anomalies, there are no discrepancies in the data, so that your machine learning algorithm can be confused. Okay, so usually there's quite a bit of time and effort spent on processing the data before you design any machine learning model. So we will go over that too. Okay, these are some very good questions that you're asking. Basically, our lecture for today is mostly based on pre-processing the data and then preparing the model, okay, designing the model. So we looked at quite a lot of work in the field, in the area of robotics, basically, such as we looked at Pac-Man, we looked at Great World, okay, by observing the environment and then interacting with the environment. So we talked quite a bit about the, from the robotics perspective, quite a bit. There's also a field kind of that's called image processing or the computer vision, because as humans, we actually can see, we can see and then perceive the environment and then see, what objects that we have observed, what are the features or properties of, the scenes that we create through our eyes. So that is actually the computer vision field, which is kind of inspired by the human vision. Okay, so which is why it's called the computer vision. field. So, and then in the field of robotics, we have seen that as humans, we can walk, we can run, we can, go up or down the stairs, walk up or down the stairs, we can climb, we can run, we can sleep. So all these properties are actually, kind of inspired from the human's perspective, and that is then designed using the robotics. And we have also seen the ant robot. So, yes, Robert.
Vision. 'Cause- Vision.
Yeah. So as I say, when we perceive something, we interpret by making a scene through our eyes, what we see through our human eye retina. And then there's a structure like human brain. The way it is trained, there are some neurons that fire up, and you interpret the scene that you have basically perceived. So computer vision comes from that field where you basically let your agent or your software perceive something in the environment and then interpret the scenes. Okay. So there is another database or data-driven technique that is very, very famous these days. In fact, in the past decade or so, it has actually skyrocketed. Deep learning. Okay, so deep learning basically mostly comes from human brain's perspective. Okay, and it has two different major branches. First, designing some statistical data-driven approaches that have been done through deep neural networks or deep learning techniques. Computer vision also comes through, or utilizes one kind of advanced deep learning technique that's called the convolutional neural network. What we basically do in convolutional neural network or computer vision is that we apply several, mathematical operations on an image that has been taken, okay, that is taken through, let's say, a camera that is mounted on a robot, or you have a vision-related application, and we perform some operations, repeatedly, recursively, we perform some operations. Something like this, in order to find any item, something like this. So you say if you have a scene where you have observed a vehicle, okay, a traffic light, and a human. Suppose that there is an image that is taken that you can, as humans, as our brains are trained, we actually look for different features and different patterns within the image, and then we identify that we have seen a vehicle, a human being, and a traffic light. We can also do that using computers. So we can take the image and we can apply several operations repeatedly, something like this. So we look for features, like we start from the beginning and we apply, we slide that window over the image and we identify different things. And then within each of this sliding window, we see that if there are some specific patterns that exist within that part of the image, then we recognize or we identify and we say that there is some sort of object that we have detected. And that comes basically through convolutional neural networks. Why it's called the convolutional neural networks is because, first of all, this idea comes from neural networks. Okay, see, all those nodes are connected. I'm not going to spend too much time on making sure that every node is connected. So the input becomes the pixels within the image, okay? And the output becomes whether we have detected an object within the image or not. And the reason why they're called convolutional neural networks is that at each node, we perform this sort of convolution on the entire image. Okay, Ronald.
So is computer vision symbiotic learning?
Symbolic learning. Okay, symbolic learning is part of the symbolic learning, robotics or computer vision. Okay, computer vision basically, you see, so when you have data in hand and you are to design a software in order to identify or recognize objects based on some sort of evidence that you provide, then it all actually is also part of deep learning, and deep learning requires large amount of data, very large amount of data. Okay.
So deep learning uses data symbiotic to create objects.
No. Symbolic learning. So symbolic learning is a different thing. So you can even perform unsupervised, some sort of unsupervised learning on images or on videos to create groups of different objects where no input is given, okay? Or you can use a lot of labeled data where you know the answer, that you may have seen something within the image, and then you tell the algorithm that if you see an object with these features, then label that as that specific object. Convolutional neural network is one part of deep learning, okay? So as deep neural networks, every node goes through a convolution operation. And we will talk about and we will go through what a convolution operation is. What is the mathematics behind that and how that convolution is done so that the computer actually understands what might be the different objects, parts within an image, okay?
So I'm kind of confused because it seems like you're going between both symbiotic and deep learning.
Yes.
To talk about how convolution neural networks are used in
Okay,
objects.
so let's make it easy. Let's not talk about symbolic learning at this moment. Deep learning, I'm talking about deep learning where you require a large amount of data to learn some patterns within an image or within a video sequence, okay? So within the video sequence, when you have large amount of data, you're actually telling your computer algorithm or your software that you need to learn some sort of objects that have specific properties. So you provide the evidence to the computer programs to learn those specific features within the data. So in order to do that, you provide large amount of data to the computer algorithm. And then you can apply convolutional neural networks. So these convolutions are actually done on images in order to identify some sort of objects based on the evidence that you provide to the computer algorithm. Let's not talk about symbolic learning at this moment. We're talking about just deep learning, okay? So there are some parts, there are some problems that can just be done using neural networks, like really simple. There is no, complex number of layers within, just like how human brains work, there are complex number of layers that are involved. Like some group of neurons, they fire up and then they provide their output to another group of neurons, then they fire up. And actually the process goes through several layers of operations. If you don't have multiple layers of operations within your neural network, that's called artificial or feed-forward network or perceptron. It's called the simple neural network. But when you have deep or more complex artificial neural network with a lot of hidden layers, where the input has to pass through all those layers, that's called deep learning. Okay, so that's deep learning. And convolutional neural networks or deep learning can be done further in two different contexts. The first thing is basically what we have just talked about is actually static learning part. There might be some scenes or there might be some problems which may have time dependency. Okay, just like we talked about Markov property, right? We said that there might be some situations in which your current context might depend on your past context. How do you solve those problems? Using an extension of typical artificial neural networks that's called recurrent neural networks. So recurrent neural networks are designed to solve the problems that have time dependency involved or time series data, in which there are current instances. Instance at current time t is dependent on the same instance that at time t minus 1 or time all the way to 0. Okay, so the recurrent neural networks are designed to solve problems for time series data, problems that have time dependency. And there's one more extension that we will study in week 14, I believe. It's called long short-term memory networks. That's also recurrent neural networks, but as part of the mathematics, we complicate the recurrent neural network a little bit, and we involve several gates. It's called forget gate and several other, mathematical operations that we perform to remember the patterns that have happened in the past, and remember basically, it's stored in the memory, and it's called long short-term memory. Okay, LSTM. They're very famous these days. Okay, I will go over a few examples of those so that they make sense. Long short-term memory. Yeah, we'll go over that part in quite detail. not before, okay? Let's talk about what we are going to focus today, machine learning, the data-driven technique. All right, so machine learning can actually be applied to solve problems in both contexts, like two major contexts, like classification and regression. Okay. Classification is when you're trying to predict something or classify something into different classes, okay, such as based on your age and your experience at work, what should your salary be, or which age group you should be, okay, based on certain properties, or like grouping, basically grouping. Let's say you acquire a large amount of Twitter data, and based on the tweets that you write, are those tweets from a political perspective or from a sports perspective, from an educational perspective? So you're kind of classifying your data into different classes, okay? And regression is when you try to predict or identify an outcome that has a continuous behavior, okay? That is a continuous behavior. Something like this, based on your age and height, what is your shoe size? Okay, what might be your shoe size? So something like this, in your x-axis, you may have, let's say, your age or height, and what might be your shoe size. And now your shoe size can be, let's say, I don't know if shoe size is a very, very good example, but the variable that is continuous, it basically has infinite number of possibilities. Your shoe size can be, let's say, 7.5, 8.5, 8.51, 8.50, 8.501. So there are infinite number of possibilities to predict or to identify or to predict your shoe size, right? So when you identify the variable that has continuous nature, okay, that's what you call regression, okay? So machine learning is very useful because as humans, we can see and process data for up to 3 dimensions. We can see in 3 dimensions, right? That's how we actually see in our environment also. So as long as we have like 3 dimensions, X, Y, Z, we can see, look, and process data pretty well. That's how we are trained. When we add more and more and more dimensions in our data, it becomes extremely difficult or impossible for us to process data in order to perform some prediction or classification, because human brains are not trained that way, okay? And it's also, so far it is extremely difficult or impossible to visualize data in more than three dimensions, okay? What's good about machine learning is that you can add many, up to like tens and sometimes hundreds of different dimensions, and it will perform extremely well on doing classification or regression or prediction. So that's basically the useful point of machine learning, is that sometimes you have data in tens of different dimensions or even hundreds of different dimensions sometimes. So machine learning can perform super well on data with multiple dimensions. As I said in my previous example, based on your height, what is your shoe size? So that's 2 dimensions. Height is 1 dimension and shoe size is 1 dimension. You can plot that. So your x-axis can be your height and your y-axis can be your shoe size. So that's 2 dimensions. Okay? In 2 different dimensions, you can plot the data. You can have, based on your height, your age, and then your shoe size. That's 3 dimensions, right? Based on the area where you live, or based on your salary, whatever, your socioeconomic factor, that's 4 dimensions. The more variables, the more properties that you involve, that's another extra dimension that you're adding in the data. So real world scenarios have more than 3, mostly they have more than 3 dimensions, okay? So when I'm talking about a dimension, it's another property, another attribute, another parameter that you have within the data, okay, another property. of a problem that you're trying to solve. Make sense, Ronald? Yeah, another measurable event, another variable, okay? We have, I'm gonna very briefly describe the difference between the supervised machine learning and unsupervised machine learning. How many of us heard about these two different techniques, supervised and unsupervised? 2, 3, okay. So supervised is basically when we teach the model or teach the machine learning model what is to identify. What is it? What is the task to do to solve a specific problem? In that case, we actually have data with answers given. That's called the labeled data. So when we have the data that has the answer with it, that's called a labeled data. We call it a label. Okay. In order to do some sort of a prediction based on your, let's say, height and your shoe size, let's say we provide basically the data in this form. Like, let's say we sample several different people from our class. We basically note your height and then we note your shoe size and we plot that. Okay, we plot that. So now we have the data. So of some people, along with their heights and their shoe size. Now, if we want to do the prediction on someone whose shoe size we don't know, and if we provide their height might be somewhere here, right? Suppose that their height might be, let's say, 6'1", 6'2". 6'1", 6'2". As long as we have this input, using this model that we have designed, machine learning regression model, we might predict their shoe size exactly, from the chart. So when we have the answered data or labeled data, that's called supervised learning. We supervise the machine learning model by providing it the data that is labeled, that has labeled with it. Okay. Something like I also very briefly mentioned the tweet classification. So where does this classification come from? In order for a computer model to identify, recognize what type of tweet that you have written on Twitter, it will require a large amount of data based on the tweets from different classifications. You have to provide it before so that it learns those kind of features and properties. And then based on those features, you let it basically do the prediction without giving its explicit instructions. The second part basically is unsupervised learning. That's where you don't have labeled data. You let the machine segment, identify different types of patterns within the data to group different categories, to cluster different data within your within your domain. Something like this. You provide a computer program the image data from Hubble telescope and say, okay, classify or group different galaxies or different planets according to their size and the distance that you have. So right now you don't know the groupings. You're telling the computer program to identify those groups, provide those groups in the beforehand in order for you to do some sort of more advanced kind of task. So that's unsupervised learning. When you don't have labeled data, you let the machine basically identify or classify or cluster different groups, possible groups that might be present in your data. And that might be very useful for your supervised learning task, right? So suppose that in the beginning, you may not know any of the groupings or any of the clusters that you may have in your data. So you let the computer program provide you an initial preliminary kind of classification or groupings of different data or clusters of different data. And based on those clusters, then you perform some sort of labeling. You say, okay, I found this really nice, distinct kind of group of data points. I am going to call it group 1. And then you look at the evidence and say, oh, wait, you know what? This group basically tells me that most of these 95% of these tweets are actually coming from a political perspective. So now I'm going to group them. Based on some sort of similarity between different features, the computer algorithm groups or clusters different types of data. That's called unsupervised. Yeah, so clusters or groups are created based on different patterns within the attributes or within the parameters that you have. It looks at all different dimensions, okay, dimensions of the data, and then groups different data points according to the patterns that it has found. And there are several different techniques that are applied, such as hierarchical clustering. We're going to write some code for k-means clustering algorithm. This is one of the most basic clustering algorithms that is, out there as part of unsupervised learning. I'm going to show you some examples of self-organizing maps that I have done in the past for several different projects. Principal component analysis, association rule mining. So these are some of the unsupervised machine learning techniques that are out there that can perform unsupervised learning. For supervised learning, we have support vector machines, artificial neural networks, Bayesian networks, logistic regression, linear regression, decision trees, naive Bayes. These are all the approaches that can perform supervised learning. Okay, and we will talk about and we will write code for decision trees, support vector machines, and artificial neural networks as part of deep learning. So we'll write the code for these. And then the third part is reinforcement learning, where you actually let your computer program or your agent interact with the environment through trial and error basis. So you let it learn by interacting with the environment. Okay. Brute force. Okay. Just think like, you're dropped into an island where initially you wouldn't know anything, like where to go, what to do, because the environment around you is completely unknown. And then slowly, in order for you to live, you need to learn what to eat, what not to eat, where to go, where to walk, where to live, how to basically interact with the environment. So that's when you let the program basically, learn based on trial and error, just like making a robot, climbing a wall without falling. Okay. We'll follow this. Okay. This workflow. I'll have a more detailed version of the workflow that I promise you in any sort of machine learning problem that you're going to solve is going to be extremely helpful. Okay. Question?
Branches. Because it feels like some of these.
So reinforcement learning can have an overlap with supervised machine learning. Okay. Because with reinforcement learning, you may have some data for the robot or for the agent to train itself in the beginning. So it may also have dependence over time. Something like, what your program or what your agent does may have some dependency on what it has done before in the past. So it may have some overlap, but these can be the major categories that you can create in sort of from the perspective of statistical learning, machine learning, or data-driven learning. So what we do is we initially have, data in hand. Okay. Using the data, we train basically the model, we generate the model, and then the model is going to use that data to learn the patterns, okay, for a specific problem. And once the model learns the patterns, you can ask your model real questions to answer some questions that are unknown for the new data that is unseen by you. So we'll talk about these three things quite a bit. Okay, let's very briefly discuss why machine learning is so important. Why it is so important. The very first reason that I am going to briefly discuss why machine learning is very important in the 21st century, especially after 2010, 2005, past that time, why it has become so important. First of all, we have generated an extremely large amount of data. Every problem through using the revolutionization of the computational power, we have a lot more better data that we have. So we have access to better data as compared to the previous century. We have access to the better, very large amount of data. And then there has been a dramatic evolution of the computational power. that we have. So machine learning, as I said, machine learning basically statistical learning, or machine learning, there is a part of machine learning that is statistical learning, right? That's based on data. We are talking about data-driven learning. So when we didn't have much of the computational power to process large amount of data, there wasn't so much of an increase or so much of an interest. But now that we have really large amount of data that is, out there through Internet of Things, through different devices, we have a better computational power, which is why machine learning has become very important. One of the hardest topics, okay? So what's the largest measure of the data that you have heard of? A terabyte, a petabyte, a petabyte, right? So the increase from one unit to another is 1024, something like this. So the smallest unit be a bit, right? And then 1024 bits makes a byte, right? So we have something like this. We have a bit. Let's say just start with a byte, okay? The next 1000 bytes is 1 kilobyte, right? 1000 kilobytes is 1 megabyte. And then 1024 megabytes is 1 gigabyte. Then we have a terabyte. Then we have a petabyte. And then we have 1024 petabytes makes 1 exabyte. Okay, exabyte. So it was said based on the survey that was done by IDC's Digital Universe Survey. Basically, this data has been measured from mobile devices, Netflix, YouTube streamings, planes connecting with the satellite stations, data coming from satellites, mobile data, TV streaming, all those sorts of communication spectrum. Through those, the data was measured, and according to the Digital Universe Survey, that is actually pretty old. It was done in 2012. It was said that up until 2000, there was about, I think, 140 exabytes of data that was created. 140 exabytes that was created. By 2005, there were about 130 or 140 exabytes that were created. By 2009, that figure went up to, I think, 7,900. And then here, I forgot what it is, but by 2020, the prediction was that the amount of data that would be generated would be 49,000 exabytes. So let me just very briefly mention to you how big this number is. Within 1 to 2 terabytes, which actually is here in this range, 1 to 2 terabytes. Suppose that the day that you were born, your parents started recording you, video recording you in high definition. And if you live for 80 years, every single moment of you recorded in high definition, high quality, it can, for 80 years of your life, it can be within 1 to 2 terabytes. Within 1 to 2 terabytes, high definition video for 80 years long, nonstop, every single second of it recorded can be fit into from 1 to 2 terabytes. Now just think of how big this number is. 49,000 exabytes. Right now, the corporate world basically is falling somewhere here. Corporate basically is using less than 10 or generating less than 10,000 exabytes of data. But the idea is to just look at the prediction and to see how much the data has already been generated. And now, because of the cloud computing and all the computational power that has been improved over the past decade or so, there is much more advanced computational power that we can have. We can perform some sort of, do machine learning to solve some real problems. And we have a really large amount of data that we can utilize. Okay, yes, Ron.
So I know that.
49,000 exabytes, there hasn't been any machine that can process, that is developed that can process.
Mostly we just take.
Yeah, so that 49,000 exabytes is actually all the data from the world combined, and it's prediction. It may be much higher or it may be much lower.
How much access?
So it depends. So if you're trying to solve like a churn rate, let's say for McDonald's, you're gonna have only access to McDonald's data from them. Maybe, I don't know how many hundreds of thousands, or sometimes maybe millions of data points every day. Maybe there might be more than 1 million worldwide burgers sold at McDonald's. You know, more than 1 million transactions, right? So you can have access to that data. So that data basically will relate to the specific problem that you solve. It can be millions of rows. Look at Facebook. There are about 3.5, between 3 to 3.5 billion user entries every day. Okay, 3.5 billion activities per day. That is that's large data, that's big data. So you may need some sort of a more advanced algorithm for that. Deep learning works very well when you have big data and you have very large amount of data. Okay, so that depends on the problem that you're trying to solve. Nathan, you raised your hand. This is from 2012. You can find a new one. Yeah.
It was like 65.
65. Okay.
So I was.
Yeah, there might be a new survey that may have done it because this was back in 2012. Okay, all right. So in very, very simple terms, for the next 5 weeks, 4 weeks, we're gonna look at a real world scenario. We're gonna have a problem in hand. We're gonna say, here's the problem that we have in hand, and we have some data, and we're gonna design a model. We're gonna design a machine learning model that might fit very well for that real world problem. Okay, how will we identify what might be the best machine learning approach to apply for a specific problem? Okay, this slide is very interesting. I can promise you that when you start applying for, let's say, your professional career, you will look for jobs, and if any one of you is interested in jobs like, let's say, software engineer, machine learning engineer, data scientist, data analyst, computer vision engineer, deep learning engineer, anything that is related to machine learning, artificial intelligence, you're going to see in the job description or in the required kind of responsibilities or roles and responsibilities, they're going to say the candidate must know the machine learning model development pipeline. So this is based on my own personal experience for several years of working on different machine learning techniques. And I've actually seen, a lot of the literature following basically these number of steps in order to design a machine learning model for a specific problem. And these are all very important steps, 5 different steps that you can basically you can have to design a well-fitted machine learning model. And that's basically the pipeline. So as a machine learning engineer or as a data scientist, you will have to design pipelines for scalable machine learning modeling algorithms. Okay, so you will see what those are. So by looking at the real world scenario, real world problem, the problem that we have in hand, what do we have? First of all, we have data in hand. You will be given some data. Okay, you'll be given some data, something like, based on the company's kind of profile for the past, like, let's say 5 or 10 years, here are the number of customers that we have, their properties, like, their spending rate, how many times they return, kind of, let's say it's for a store, right? For a store, you say, How many customers, like what is the regular customer, how many times they come back to the store, what are specific items, what are the specific items that they buy, et cetera, and what might be their expected, spending at your store. You have to predict what is the expected spending at the store that you have. So you're gonna be given some data, okay? The first step that you will have to perform is actually pre-process the data. The data that you are gonna be given is not gonna be in a form that basically a machine learning algorithm completely understands. Let me tell you what it means. So you have, let's say, parameters like x1 to xn, and then you have an output. What is x1 and x2, xn? These are like, what specific item? Each parameter, each dimension. When I said that based on the height, predict the shoe size, these are the two dimensions. X1 basically is the height, an input parameter, and then y basically is a dependent variable. So these are different dimensions of data. You will be given some data and you will have evidence, but in some parts, you might have the data that is missing. You don't have any information about that. Because the data collection was not done, let's say, or was done as best as possible, but there are some parts that the data is not even provided. Ronald.
It's kind of like, can it be biased? Can it create bias?
Yeah, so you have like skewed distributions in the data. I'll come to that part in just a few moments. Okay. So there are almost always the chances that your data will not be in an exact form that you will require to simply feed it to a machine learning model. Nathan.
Seen 2020, about 40, which is where they were at, to like 70, like this is 60, 70. And there's
Yeah.
one study I'm looking at on.
So within these 8 years, they have more than 20,000 zettabytes have been generated.
So
Yeah. Mind-boggling. Okay, so a mind-boggling number. Okay. Yeah, yes. So, okay. So in that case, what you will have, so deep down at the core of each machine learning algorithm, it actually performs some sort of difference, like distance-based or similarity-based. The common types of distance-based measure is Euclidean distance. Remember Manhattan distance that we have covered, or Mahalanobis distance. Okay, they actually perform some sort of distance-based measure to do some sort of processing to design a model. Or in terms of the similarity for categorical variables, you have, let's say, cosine similarity, Hamming distance, or Hamming index, or Jaccard index. I'm just mentioning those. Right now, there's no need to worry about or remember any of these. But if you see deep down at the core, the machine learning basically is going to perform some sort of this difference. Like when you have two rows, two data samples, it's going to calculate the distance between these two based on some sort of a formula. So you actually will need either numbers or some sort of letters. It's some input. So in order to apply any machine learning algorithm, you need to have data for those parts that are missing. So then you will have to pre-process the data. So in the missing fields, sometimes what you would do is, for this, you look at all these rows for just this specific attribute, get the average from the numbers that are given, and fill in the cell with the average. Or sometimes you fill in that cell with the missing value with the most frequently occurring value. Some sort of processing that you will have to do. There might always be the chances when you will not get the data in the format that you would require. Your machine learning algorithm will not even apply on that. So you will have to perform several kind of pre-processing. Okay. There might also be sometimes there might be chances that this parameter may have range from 0 to 50,000. Let's say like the numbers appear in that column range anywhere from 0 to 50,000. Okay. And your immediately next column, it may have only values from 0.5 to 2.7 only, something like that. The range is like really, really kind of small. What you will have to do is sometimes you'll just have to normalize the data. Normalize all the columns between 0 and 1 to make the machine learning algorithm be more comfortable with the data and perform the computation much more easily and much more efficient. Run it. Yeah, cosine similarity. Okay, so you will have to normalize. What you will have to do is using simply this formula, current data point minus x min divided by x max, x min. This will simply normalize your data between 0 and 1 very, very nicely. What do I mean? Xi is the current data point, which is this. You get this current data point, you subtract it from the minimum value from this, which might be 0, and then divide by maximum from this column minus minimum of this column. It will just give you, normalize the data for you between 0 and 1. So sometimes you will have to normalize the data for the machine learning algorithm to work better, more efficient. So you will have to perform these pre-processing techniques before you even get to a machine learning algorithm. All right. Then you design the model. Then you develop the machine learning model. Okay, so in order to, for a relatively new machine learning engineer or newer data analyst or data engineer, here's a mistake that they make. After doing the data pre-processing, all what they do is they apply several different machine learning algorithms, and then they say, this is the approach that has given me the best, kind of prediction and best performance. Therefore, I'm just going to go with this. The mistake that they make is they actually don't look at the data itself. The machine learning model needs to identify, it has to be robust, and it has to have a trade-off balance between the complexity of the model itself versus the generalizability. This is very important. You will have to remember. And how you can do this? By simply doing the exploratory data analysis. This is something that is very important. You have to basically look at each attribute, each dimension of the data that you have. Look at the dimension, find out what dimensions or what parameters are actually correlated with each other, right? What are the parameters that you might just remove, drop from even model development? Because there might be another attribute that is going to be exactly the similar as one attribute. So you can drop one of those, or you can combine the two of those to simplify your model much better, to simplify that. Therefore, exploratory data analysis is extremely important. This is what people miss most of the time. And I can tell you that this is one of the most important steps, because in this, you can see pairwise correlations and see what data is more appropriate for model development. So then you do the exploratory data analysis, and finally you do the model development. You're going to have to evaluate the model. Typically, what happens is, let's say you are given, let's say, 100,000 data points, 100,000 different tweets, 100,000 different tweets with the label. Suppose that in different tweets, let's say word 1, word 2, up to word n that you have, and then you have the category. Is it a political tweet? Is it a sports tweet? Is it a, what else? What other tweet that you can have? Sports, political, that's the only two I know. Fashion, music, right? Clothing, textiles, etc., etc. You can have that, right? Usually what people do is, when you do machine learning, you do, oh boy, at 80-20 split. You have 80% data that you expose to the model. You design the model based on 80% data, and then you keep 20% data. You keep that. You don't even show it to the machine learning model. From this, machine learning model learns that the trends, basically this Y or Y category, Y. And then you provide the model with this data by not providing the Y, and you predict Y hat. You predict the category. So once you predict the category, you compare it with the actual category and then see how good the prediction is. You compare those using either R squared, mean squared error, absolute relative error, etc., etc. Okay. And then you finally do the hyperparameter tuning, meaning like you tune the parameters based on the evaluation. You see if your R squared is not that great, you will basically tune the parameter of the model in order for it to improve force prediction. So usually there's an 80-20 split that is done in the data to perform machine learning. Wow, I ran out of time really quickly. I wasn't able to talk about the support vector machine and decision trees. I'm going to go over very quickly. So classification basically is a sort of technique that basically creates a distinction between two different classes. A positive, let's say, a class, and a negative class. So the line that you're seeing, a classification algorithm actually draws a line that perfectly, reliably distinguishes, creates a distinction between two different classes. I'm saying two different classes here. Your data may have multiple classes. So right now I'm only talking about two dimensions, X and Y. And then there is a line that distinguishes between the two different classes. You can have multiple classes, something like this. You can have like this, and you can have the data. And then you say here, you can create a 3D distinction. You can fit a hyperplane instead of a line. In regression, you simply just fit a line. Fit a line within the data where your data is continuous, okay? There are three different forms of regression, linear regression. I hope that everybody understands this equation. Why? What's that next level? Slope and y-intercept, right? I hope that everybody understands. So the idea basically is to fit a line that represents the data best or fits that data as best as possible, right? That is the least squares fitting. How many of you have heard of least squares fitting? Least squares. Okay, all right. I'm not going to explain what least squares is, but basically, you know, a model basically could have drawn this line too. The idea is to look at the error, how far each data point is from that prediction line, and see what is the error rate. So you have to fit the line that has the least error. You can also have multiple linear regression. There, it's only two parameters. Here we have multiple parameters from x1 all the way up to xn. Multiple linear regression. Linear regression, you're not going to have any power in the parameters that you have. X1 all the way up to xn, there's no power. There's no x to the power 2, there's no x cubed, x4, etc., etc. If you try to do linear regression on this, it's not going to work well, because all what you're going to do is you're going to fit a line like this, and your error rate, least squares error, is going to be really high. Well, you can do polynomial error. Not polynomial error. Polynomial regression. Polynomial regression will give you something like this. And in that case, you will see the power, the degree. The more power you have, the more complex, you know, relationships that it will find. Okay, I'm going to have this, explain this slides, the support vector machine, and then I'm going to explain decision trees on Wednesday. Because on Wednesday, there's no slides, I promise. There are no slides, no theory, nothing. All what I will do is I'll just write the code for you guys and to implement support vector machine and decision trees. And hopefully everybody will stay with on Wednesday. All right, what support vector machine does is, as I just said, that it actually draws a line that distinguishes between two classes or more than two classes. But what it does is it does it very smartly. First of all, it draws the line, all right? And then it pushes basically, this is called the maximum margin separator. It first draws the line between two different classes, and then it pushes basically the region. It keeps pushing the regions, these two regions, until these regions hit an instance of each class. So it will go this way, and it will keep going, expanding this margin as long as it, all the way until it hits the one instance of the class. And then it pushes the margin in the other direction too, so that it hits basically the first instance of the other class. It's actually both non-parametric and parametric techniques. And the idea basically is your support vector machine becomes an optimization problem. What do we mean by optimization problem? Maximize this region given some constraints. Which makes support vector machines an optimization problem. So the idea is actually to maximize that 2 divided by L norm of W. So W is this region. Okay, let me tell you why it's one of the most powerful techniques. It was basically designed by, I think, a Russian guy back in the 90s. All right, so the reason why it's one of the most powerful techniques, because it only looks for these instances. Okay, anything that falls in here, the support vector machine or the model does not need to remember this. Now, suppose that you have a classification problem to identify, let's say, oranges and apples. It goes after the extreme examples. Something like this. Sometimes you might have a lemon that is actually like pretty big, and it might look like an orange. Sometimes you may have an orange, but by its color, it may look like an orange. So it goes after those extreme examples. These extreme examples. This might be the lemon that might look like an orange. Okay. This might be an apple that might look like an orange in here. Okay. So it goes after those extreme examples, which are the most difficult to predict or to detect, and then it only has the information about this. If it's a normal orange, it will fall somewhere here. No problem, nothing. Anything that is here or behind this point, fine, it's just going to be an apple or orange. This is why support vector machines is called the rebellious algorithm in machine learning, or the most like resistant algorithm. It's one of the most powerful techniques to perform classification or regression when your data set is extremely small, because it only looks at the extreme examples, which is why it's called the rebellious or the resistant technique. So I'm gonna stop here. I'm going to actually go over decision trees on Wednesday for the first 5 or 10 minutes, no more than 10 minutes. And then we will write the code for support vector machine and decision trees on Wednesday, okay?